Okay, our next speaker is Gerben Oling from NBI Copenhagen. Please, Gerben.
Hello, thanks a lot for the opportunity to speak here. So I'll talk to you a little bit about non-relativistic strings and how they appear in particular limits of ADS-CFT. So this is related to the spin matrix limits that you heard about a few weeks ago from my colleague Stefano. And that is a particular limit of n equals 4, where you on the cylinder, where you zoom in on the dynamics near a BPS bound. So if I write the isometries of the S3, the commuting isometries with Si and the R charges with Ji, you can build a particular BPS bound using a charge like this for combinations of those charges. And then the spin matrix limit consists of zooming in by taking lambda to 0, but keeping n fixed. And this combination here also fixed. So effectively, you're zooming in on a particular part of the one loop spectrum of the dilatation operator. So you can do this in principle for any n, but in this talk, I'll focus on the large n and large q limit, where this gives rise to non-relativistic sigma models. So in particular, if you take q to be J1, J2, just two R charges, then you get the SU2 Landau-Lifshitz model in this limit. And this is similar to the limits that have been considered by Krutchensky and others at earlier points in the literature, but it's not exactly the same limit. So the question that I want to talk about in this talk is if you can do something similar on the bulk side. So in particular, if you can get a sigma model like this as the sigma model of a particular non-relativistic string coupling to a non-relativistic geometry. So let's do that. So in the bulk, this has been figured out recently in a series of papers. And it's basically the same idea. You select a spin matrix limit by choosing a particular BPS bound to zoom in on. And in the bulk, that corresponds to choosing a particular combination of isometries of ADS5 times S5. And so this is the limit in the bulk variables. Okay, so if you fix, for example, again, Q equals J1 and J2, that leads to what you could call a SU2 spin matrix string. So actually corresponding to this choice of charge is a choice of coordinates. You can parameterize ADS5 times S5 in those coordinates. And then taking the spin matrix limits restricts the dynamics of the string to a particular submanifold where a combination of these coordinates becomes null. So that's what I've written here. That's the reduced metric of the resulting four-dimensional, in this case, submanifold of ADS5 times S5. And it turns out that metrics with a null isometry you can always use to give you this non-relativistic Newton-Cartan geometry that I've written here. So this is just a very general way to give a parameterization of a metric with a null isometry that leads to non-relativistic geometry. So in this particular case, for the SU2 sector, you get something that essentially derives from the Hopf vibration of the S3 inside the S5. So the spatial metric in this Newton-Cartan language that determines the distances in space is given by just the Fubini-Soddy metric on the base S2. And what sometimes is called the mass potential is given by just the Hopf potential. Okay, so this is the geometry that you get for this string in the bulk. And you can do this for all different kinds of spin matrix limits. So we worked out some kind of dictionary for this. For example, if you take J1, J2, and J3, you would get the SU2-3 sector, which corresponds to having a spatial metric as the base Fubini-Soddy CP2 metric of the whole S5. But there's various other combinations that you can look at. Okay, so the action of this string, I unfortunately don't have too much time to talk about, but in the light cone gauge equivalent version, it looks like this here. So that is determined by this M field that I just showed you in this spatial metric. So if I plug in the ones that I found for SU2, you actually reproduce this Landau-Lifshitz action that you get in the corresponding limit on the boundary. But okay, if you're familiar with Newton-Cartan geometry, you might notice that these fields play a slightly different role here in this action than they usually do. If you're not familiar with Newton-Cartan geometry, that's also fine, but we can stare a little bit at the action on top of this page. And you might notice that if you would think of this as a phase space action, also an Hamiltonian phase space, then this usually determines the symplectic form or the Poisson brackets of the fields on this phase space. And in fact, the exterior derivative of this M form now gives you the symplectic form on that phase space. So what people sometimes call the mass, in this case, determines the phase space structure. And this H metric is something that gives you the Hamiltonian out of this action. So okay, that's just interpretation at this point. But you can actually do something useful with this, and this is kind of the idea that I want to sell in this talk. So looking again at the SU2 case, you get the Landau-Lifshitz model. And you can try to quantize this, of course, in terms of these theta and phi coordinates, but it would be quite hard. The propagator that you get from here would be something with 1 over sinh or the Poisson bracket. So that's obviously not something that's going to give you a very nice time in the quantum theory. Instead, now that you know that you can interpret this as a symplectic manifold, as a sphere in this case, basically, you can just use the Darboux coordinates to reparameterize your fields. So the Darboux coordinates on the sphere are something like this, and then the symplectic form just diagonalizes. You get canonically conjugate variables. So if you rewrite the action using those variables, I can introduce this Schrödinger type field out of a complex combination of these conjugate variables. You get something like this. I've actually truncated the expansion here. But okay, the leading terms turn out to give you a Schrödinger type propagator. And this propagator has the nice feature that if you have a closed loop of these phi fields, the diagram vanishes. So if you then study, for example, the 4-point function, it turns out that only a very limited class of diagrams can actually be non-zero. And what's more, as Klose and Zarembo showed in this very nice paper, only the 4-point interaction then actually matters. So all of these higher order terms I can just throw away. And that's how they managed to compute the exact S matrix for this SU2, for this Landau-Lifshitz model. At least to me, when I was studying this paper, this choice of coordinates seemed a little bit mysterious. But I want to advocate now that you can use this symplectic perspective also in the other spin matrix limits where this computation has not been done already. So the idea would be to find the corresponding sigma model, which reproduces in, for example, the SU11 or the SL2R case sigma models that were already found in these Krzyzewski type limits. You could do a similar coordinate transformation to the Darboux coordinates that are appropriate to that situation, and then find the resulting class of diagrams that contributes to the 4-point functions. And since all these models are expected to be integrable, they're just subsectors of the one loop dilatation operator, you should be able to generalize this Klose and Zarembo computation to other spin matrix models. Okay, just to recap a little bit, these spin matrix strings are basically the bulk equivalent of the spin matrix limits that Stefano told you about, that you could also read from them about on the archive today for a new sector. They couple to a non-relativistic geometry that is a variant of Newton-Cartan geometry that you might have heard of. But in this case, the remarkable thing is that this geometry effectively parameterizes the phase space of physical excitation. So it's not perhaps a target space in the normal sense of what you're used to for string theory. It really defines gives you a Hamiltonian and a symplectic form directly from the geometrical variables. There's a couple of things that we want to do with these models. As I mentioned, I would like to extend this computation of Klose and Zarembo to other models. But purely on the string theory side, I've only shown you the light cone gauge fixed action, but there's actually something like the Virasoro symmetry for these models, which is the Galilean conformal algebra. And we want to covariantly quantize those and see if you can have anomalies on the world sheet like you have for normal strings or in the global symmetries. Finally, the non-compact sectors turn out to give you geometrically quite something interesting, and we're trying to see if you can get holography directly from those as well.
Thank you very much. Let's thank the speaker. And questions, please.
All right, I can ask them. So if you quantize, so you said, okay, so let's have these coordinates, we can quantize and so on. So will you then get the spin chain if you quantize this model or what? Because this model can be obtained as a classical limit of spin chain. So if you quantize, presumably you should reproduce, say, SU2, say, speaking about Landau-Lifshitz one.
Yeah.
Will you reproduce?
So at this point, I guess I'm already in the continuum limit, right?
Yeah, but presumably if you quantize, I mean, at least one of the quantizations is a spin chain. Will you get something else?
I'm not sure exactly what you mean by, I mean, geometrically, I understand these coordinate transformations in terms of these coherent coordinates that,
yeah,
that you get from the spin chain. How would you translate that?
That's the way you derive it from a spin chain. But now, okay, you are given some model, you quantize it, right? Forget about any spin chain background. So if you quantize it exactly, and you know how to, say, compute its quantum spectrum, will you see back the spin chain, or what will the beast be?
You mean in terms of the original Hamiltonian?
Yeah, so if you take this classical model and quantize it exactly and compute non-perturbative spectrum, what will it correspond to?
Sir, can you point me to which model exactly you're referring to? Because the one that's on top of the page here, that.
Yeah, for example, it is Landau-Lifshitz, isn't it? Yes.
But you're asking about discreteness of reproducing discrete results for the spin chain? I mean, it's just the continuum limit. Huh? So you've taken some, you know.
I'm trying to, say, decode this logic of Ben. I know it, Ben here, right? That if you like quantize, then it should kind of remember about discreteness of underlying exact description in terms of spin chain. That was the claim for the fish chain, fishnet.
Okay, I'm not familiar with that, but it could be that this choice of coordinates still translates to a convenient parameterization of the original, raising, lowering form of the original Hamiltonian.
Can I ask a different question? Have you thought about including fermions in this setting?
Yeah, so actually the part that I maybe jumped over a little bit, the derivation of the Polyakov action version of these non-relativistic strings, that we don't know how to do for including fermions at the moment. Which is not to say that it's not possible, which we just haven't thought about that yet. The geometric statements I made, of course, apply only to the bosonic part.
Because, you know, fermionic versions of Landau-Lifshitz are known, and it's known how to get them from the Green-Schwarz action and so on. So,
right. Now, when I say that we match, for example, with the SU112 sector, we get exactly the right bosonic part of that classical action back. I mean, the first thing, if I personally would start with this first bullet point, I would just do SU11 and be happy that I only deal with bosons so far. But it would certainly be interesting to extend this to all the other spin matrix limits have fermions in them, of course. So.
Well, yeah, especially since you're asking these questions about, anomalies and so on.
Right. But the funny thing is that some of these, there are SU2 and SU11 spin matrix limits that just don't have any fermions, and that should, well, I'm not sure if these extensions appear in the world sheet, but if they appear, they should allow us to be critical in 4 dimensions in this weird non-relativistic sense. So you don't necessarily need fermions for those, is what I mean. But of course, we should include them eventually.
Okay, thanks.
So just like the last bit of my question. So does this model have a meaning by itself at the quantum level, do you think, or it just effective model?
Well, from the field theory side, these models exist for any n and for any values of the charge. So yeah, so those are known in earlier papers of Klose, but I don't know at the moment how this coordinate choice would map to that, if any. But it would be interesting to figure out.
Right.
It is a double scaling limit of the spectrum of the dilatation operator, right? That it should reproduce if you quantize it. So if I understand correctly, I think that
Right.
the meaning, the qualia, no?
Okay, we are now in illegal territory.
Okay, sorry. We can continue the discussion.
We discuss our break.